Okay, thank you everyone for coming to the morning session. Before I introduce John, I'd just like to say that the second talk will be over Zoom. The reason is that all flights from Israel have been canceled, and we're actually not going to live stream it because there's a chance of an air raid during the talk. So just, FYI. So it's my great pleasure to introduce John Kleinberg. As everybody.
Live stream that Don is going to follow here, right over there.
There was a question from the audience. Am I worried that the live stream will somehow teleport the bomb? Is that the question? No, it's just, just so people don't get overly concerned. So, but yeah, that's the decision. But yeah, so it's my great pleasure to introduce John Kleinberg. We all know many things about him. As I think many of you know, he's kind of collects awards as kind of like a fun pastime, the way I sort of go running and go cycling. Just kind of two of the main ones that he's gotten that a lot of people know about are the MacArthur Award, which has some sort of nickname associated with it, and also the Nevin Linna Prize. And he's a professor at Cornell, and I would say a long-term supporter of Cornell. He not only went there as an undergrad, he also manages to drag his brother to go to Cornell as well, both as faculty. And so if you look across Kleinberg's work, he has a lot of interesting things he's done in a lot of different fields. And I think one way we can summarize a lot of it is that he sort of looks at technology, not just theory or math or science, but he specifically looks at technology all the way back looking at the internet in the early 2000s, late 1990s. And he tries to extract simple principles that actually have a very general audience message. A lot of his papers can be communicated to basically anybody. And I would just like to tell one of them that I think is lesser known, and it's work that he had on clustering a long time ago. And for instance, there his goal was to say, look, a lot of people are formulating clustering algorithms, but we don't even have a good agreement on what a loss function for clustering should be. Whereas for all of the other machine learning, the common paradigm now is just to reduce it to a loss function in PyTorch and that pipeline. And he gave this very clean paper that, again, can be explained to basically anybody on the planet that says, if you take some of the standard things people say they want out of clustering, you can't put these together into a single loss function. You get a contradiction. Just a very clean paper, and he's done that in many fields. So in today, he's going to tell us about sort of something like that for LLMs.
Okay, thanks very much. All right. Well, yeah, thanks everyone for coming, and thanks for the invitation to take part in this workshop. It's been really really thought-provoking, just all the different things going on here. I mean, I certainly find this is a topic where just the more people's perspectives I hear, the more the more I find myself being led to new interesting questions. I think it's just sort of a moment that's really expansive, just in terms of the kinds of things that we can be asking, that we should be asking, and appreciate sort of all the all the interesting work I'm coming across here. I want to talk about some joint work I've been doing with my longtime co-author Sendhil Mullainathan, who's a behavioral economist. And we were thinking about, large language models, as many people were. And one question that we sort of were starting from was that obviously the phenomenology of them is, the thing that has us all here, and it's genuinely amazing. But because the phenomenology is so interesting, we often think about the process, the algorithms that are doing this. And in computer science, often when you find yourself sort of fascinated by the algorithms, it's always good to pause and ask, can we at least write down the problem these algorithms are trying to solve? So let me start from that question. What is the problem that large language models are trying to solve? Now, of course, I think it's a cliche and talks about large language models to bring the large language model itself in as a character. So I will indulge in that cliche and use the ethnographic method here. We could ask ChatGPT what problem does the thing it's trying to solve. Now, in particular, the training. What problem is LLM training trying to solve? And it does a nice job of summarizing, I think, what it has found on many, many web pages, that the primary objective is to learn a probabilistic model of language that can predict the likelihood of a sequence of words or tokens given a context. Okay, so let's start from that, right? In a probabilistic sense, from a large collection of text, let's build a model that can accurately assign a maybe conditional probability to every possible sequence of words. And then, what we see on our screens is that we're using this model to produce strings with high assigned probability. But I guess the question that Sendhil and I wanted to ask was, if we're really, we have this window of time and we can actually still ask the question, like, what is the actual problem trying to be solved? And this is certainly reasonable. I mean, I'm not here to debate that we should be, this is a good thing to be using. But it feels like it'd be instructive to sort of ask, what is the actual simplest way we could state the problem? Because the actual problem, you could argue, doesn't actually have probability in it, right? That was our implementation decision to put probability into it. The question didn't have probability in it. The question was just, design an algorithm that observes strings from an unknown language and eventually begins producing valid strings from the language that have never been seen before. Right? If we're going to write down a statement of the question, now, I'm not going to get hung up on my exact, I'm not going to sort of get into the kind of constitutional law of the exact, text that I wrote here, but I'll try to turn that into a formalism in a second. But the idea is like, let's just sort of sit with this question of, could we ask the question without probabilities? We're sort of in and obviously we're not the only people who are doing this, in the sort of premise of the panel yesterday, one of the sort of high level categories of approaches is formal language theory. And you can say this is kind of a formal language theory approach. But so I wanted to sort of sit with this question, and let's just kind of play with it a little bit here, right? So for this abstract formulation, right, the goal is to output strings. String is so let's lean into the formal language theory take on this. String is a sequence of symbols from a fixed alphabet. A language is just a set of strings, right? If you want a running example, design an algorithm that observes programs, like it sees lots of C programs. Eventually, it just begins outputting C programs. Okay. All right. So that's the abstract formulation. It turns out if we do this, right, we end up getting some concrete questions. So first of all, this seems too general to be useful, right? How can an algorithm accomplish this? And there's a formal reason why it might seem too general to be useful. And that goes back to a theorem of Mark Gold from 1967, right? So this is now, right, this is not the 80s or 70s, this is 1967, a very long time ago. And he was interested in this language generation question, right? So this is in the era of sort of where classical recursion theory was, interacting more closely with CS theory. And in Mark Gold's model, which Gold and Angluin 12 years later actually completely characterized in a very nice stock paper, the adversary thinks of a secret language, let's call it K, that is known to be produced by a representation from some countable list, right? So we know it's produced by a context free grammar, or we know it's produced by a finite automata, we know it's produced by a linear space-bounded Turing machine. There's some countable list of representations, each finite in size, that could be producing it. And our goal is to find that language. Maybe cleaner, I don't really need representation. So for most of the talk going forward, I'll just say K is known to be one of L1 or L2, L3, a countable list of languages, all context free languages, all regular languages. And if we use this view where we don't have representations, then I guess we imagine there's just a black box that I hand it an index I and I hand it a string W and I say, is W an Li? And that's just my interface to it, right? So one computational step is either a usual computational step or one of these queries. Okay. And an adversary and the algorithm play the following game. The adversary enumerates the strings of K one by one. Repetition's allowed, but that's not going to be really an issue. But crucially, each string of K must occur in some step of the enumeration, right? It wouldn't be fair of the adversary to like hold back an infinite subset of K and then expect you to guess the answer. It didn't actually tell you the language, right? And in each step, the algorithm guesses an index that's like, I think the language is L sub IT. And the algorithm wins if there's some finite step T star such that its guess IT is correct in every step onward. In that case, it has, in Mark Gold's terminology, identified K in the limit. Now, obviously, the algorithm is not required to know when it has succeeded. And obviously, the way these recursion theoretic arguments often work is that you sort of have to win without knowing exactly when you've won. So, but after some finite time, its guess is correct forever. Also, multiple of these languages could be the same because after all, there are lots of context free grammars, for example, that produce the same language. So it could bounce around in its indices as long as it's always producing the right language up to time. Okay, and so that was the question Mark Gold asked. I'll mention a couple of things about this model. Yeah.
Depend on the
yeah.
index.
It can depend on the index and it can depend on the enumeration. because the adversary could hold back crucial parts of K as long as it wants. And so you sort of have to wait for that to happen. Yeah, but nonetheless, it's still, even if T star depends on every one of those things, it still has to be some finite time after which you're correct forever.
I think it has to be.
Yes. Yeah, great. Yeah, great question. Now, Mark Gold's paper is interesting to read. And he actually motivates this model in part by language acquisition in infants. Because he says, notice three things that make this problem hard. Like, one, the algorithm never sees, imagine you're like an infant learning language. To first approximation, you don't hear a lot of dramatically ungrammatical sentences. Sure, you hear grammatical slips, but you basically hear correct language. If you're under the age of like 12 months, you're sort of forming guesses about what the language is, but you're never told if your guess is correct because you can't actually verbalize. And you also can't do active learning. You can't ask, is this because you can't verbalize, right? So that's true for this model also, right? It's only seeing positive examples. It's never told its guess is correct, and it can't query. I mean, this is crucial. It can't query the secret language. Obviously, it can query, languages in this list. That's a very different thing. That's just the representation of the languages. Okay, fine. And so this feels like too much to hope for. It is too much to hope for. So Gold's theorem, 1967, is there is no language, no algorithm that can achieve language identification in the limit, even for very simple collections like all the regular languages, right? So any collection rich enough to have the regular languages, you cannot achieve identification in the limit, right? Or if we want to write the contrapositive, for every algorithm, there is, right, from say the regular languages, an adversary can pick a K and an enumeration of K after studying the algorithm adversarially that causes it to make infinitely many mistakes. And then 12 years later, Dana Angluin actually characterized exactly the language collections for which an algorithm can perform identification limit. They are very restricted, like very, very restricted classes. Okay. So, I mean, it's fine. It seems like we were asking this worst case, just as an adversary, it says things. It felt like too much to hope for, right? And putting structural restrictions on doesn't help. Even just the simplest, even like arithmetic progressions, basically, it's too hard to eventually learn the limit. I don't know which arithmetic progression I'm looking at. And so the focus inevitably turns to probabilistic assumptions, which is sensible, right? Obviously, if there's probabilistic structure in your data, there is absolutely no reason not to use it. So we're not debating this, but it sort of makes sense. And yet, there's a funny thing here. This wasn't actually the question we were asking. And this is sort of where Sendhil and I started from. We were sort of looking back at this literature, which we had learned about in grad school. We weren't asking about language identification. We were asking about language generation, right? We were saying, you want to observe the unknown language and eventually begin producing valid strings from the language. No one told you had to actually ever figure out what the language was. Nor is there any indication that some giant language model actually, quote, knows what the language is. It's producing strings. It's not trying to. So what if we actually leaned into that distinction, okay? All right, so new game played between an adversary and an algorithm. So starts out like before, thinks of a secret language K known to be from this countable list, all context-free languages, whatever. It enumerates them one by one, repetition allowed, that's the same. And up to some time t, it's enumerated S sub t, some finite set of languages, finite set of strings. Now we're going to change the problem, okay? And so if you've just joined us at this moment, this is the actual problem, so we're all set. Okay, so new problem. I don't have to guess, right? We used to have this communication. String comes in, index goes out. String comes in, index goes out. New plan. I don't have to guess the index. I have to output a new string from K that has never been seen before. Okay? So in step T, the algorithm outputs a string A sub T that should come from K minus ST. Right? I can't just repeat things I've heard. That would be not interesting. Yeah. But it should come from K. And as before, the kind of Mark Gold infant language learning principles apply. We don't see negative examples. We don't get feedback on whether we're right or wrong. We don't get to ask questions. Also, here I'm going to assume the L sub I are infinite because the problem in language generation does not tend to be that you ran out of things to generate. So we're just going to assume you have an infinite supply of things. Okay, and now new definition of what it means to win the game. The algorithm wins if there is some step T star such that the thing I output is always from the language for all T greater than or equal to T star. Then we'll say it is generated from K in the limit. To our surprise, and I've now asked people who were around when Dana Angluin was working on these things, like, to our surprise, it does not seem like the literature asked this question, maybe just because generation at the time was just not on people's minds. But so the question is very simple, but somehow it didn't get asked.
It asked recognition, but we asked generation.
Asked identification, but not, yeah, exactly, but not generation. Exactly. And so Sendhil and I ask ourselves, I wonder, does Dana Angluin's characterization still apply? Like, is it the same characterization? The language classes that can be identified in the limit are the same ones you can generate from the limit, or is it going to be something else, right? That's kind of the question that you might ask. And the answer turned out to be rather different from the case of identification. So here's the theorem, which was way stronger than we thought was going to be true, which is that there's an algorithm property that for any countable collection of languages, L1, L2, L3, I mean any countable collection of languages specified by just a black box we can ask, in any enumeration the algorithm can generate from k.
To identify, you can generate.
Yes, things that are possible to identify you can generate.
Do you assume the language is infinite?
Yeah. Language is infinite. Yeah. So you're not going to run out of strings to generate.
Just to clarify, when you say algorithm, you actually mean computable algorithm with that oracle, not just
I'm going to do it in
rule.
Yeah, I'm going to do it in two steps. The proof. Eventually, I mean algorithm. The
negative result was for any rule.
Any rule. Yeah. Right. So the gold result was really, I'm allowed to write down a function that takes arbitrary sequences and spits out a new word, an index, basically. And it doesn't matter if it's computable or anything. And it's still impossible because essentially what's not known is the adversary has a secret that no matter how hard you compute, you can't know. So it's going to be easier to prove it if I allow a rule, not an algorithm. But eventually we're going to kind of dismantle things a little more and actually get an algorithm. Yeah.
Just to make sure I understand the previous slide, we're not going to require that the learner can eventually generate every string in the language. Just
not going to require that. Exactly. Everything's going to generate, but this runs for infinite time, so they will have to output an infinite subset of language.
Yeah.
And actually, we can do this two ways. We could say you have to generate without repetitions. We can handle that. Even if you did generate with repetitions, like you pick your favorite string and just keep saying it, eventually the enumeration is going to wash over that string. You have to move on. So you're going to get kicked off of your favorite string infinitely often, and so you'll have to do that again. Yeah, so, okay. So that's the point. It turns out language generation and language identification are really rather different, right? Generation just says, after reading a lot of C programs, begin outputting valid C programs that are new. Identification was, after reading many C programs, output a valid grammar for the C programming language, right? These are two, as it turns out, different things.
Creating minor modifications of the string capacity that never create something very, very different.
Genuinely new. I mean, depending on the language, right? So the problem is your minor modification might not be in the language, right? It could be that my languages are all strings of, if the strings of the language are indexed U1, U2, U3, and so forth, maybe it's all the things with prime index, right? And then I can't just go, oh, let me just add one, right? Not prime. So yeah, it's a little worrisome. Now, I will say, one thing is, the original motivation for this whole thing was we're interested in languages that have finite representations, and therefore there are only countably many of them. Right. The fact that this is a countable set is crucial. If I said it could literally be any subset of all strings, then this is a hopeless task. For almost a sort of reason I can give you in one sentence, which is the adversary outputs some stuff, you generate a string, it says, nope, that wasn't it. In fact, all my future strings are just going to be from some larger set than what you've generated. That would obviously be a perfectly nice adversarial strategy, but then the adversary's contract with you is, I'm thinking of from a language from an uncountable list, and that's just we're in a very different world there. Right, so it's key that we had a countable list motivated by things like it came from a finite grammar, it came from a finite automata, finite direction. Yeah.
So this is a countable list, but like L2 could be the non-holding language.
Yeah, no, these are arbitrary, yeah. Yeah. As long as I have a black box where I can say, is string number 5 in language 2, I'm good. Yeah, no, it feels like two. Obviously, it does feel like two. Like this is not the theorem we set out to prove. It's just that we kept trying to constrain what was generatable, and we kept getting bigger and bigger things, and we ended up here. So, but hopefully, maybe by the end, I will have convinced you that this is actually.
So, is there any uniqueness issue? Uniqueness of K?
No, there could be several languages in here that are all K. That's okay. Yeah. Yeah. That's fine. Yeah. Yeah. So let's see how this. Okay. So right, obviously, a couple of things people brought up in the questions. The algorithm only needs to generate from an infinite subset of K. It doesn't have to generate all of K. It does, like, if I'm saying, like, what do I? In the end, this result is, and we'll see, it's almost kind of recursion theoretic in the way it works. And so you could ask, like, what are we learning about, like, I mean, one is that it just strikes me as this is an interesting fact. Like, this is a fact we ought to know if we're going to think about language generation. But there are a couple of places where you might see parallels once we get into the proof. Like, one is that fundamentally the proof is about the tension between two things that do go on in language generation, however you implement it, which is a tension between validity, let me call it validity and breadth. right? Validity is I should only generate valid strings. Breadth is I have to actually represent a large subset of language. I can't just stick to like a few things, right? And we see validity breadth trade-offs in a lot of places in language generation, right? Obviously, hallucination is part of the spectrum between validity and breadth for generative. Mode collapse at the other end in generative models is a problem of like not sufficient breadth. And so the algorithm that we have is going to almost seemingly inevitably is going to start out with some invalid strings. You know, it doesn't have to, it just has to generate correctly in the limit. Eventually it avoids these, but then as it goes, it settles on these increasingly thin subsets of K. It gets narrower and narrower in what it's willing to generate. As long as it can keep generating infinite sets, it'll be okay. Obviously, that doesn't give you any real insight into what's going on here. Okay. One more theorem, then I'll start talking about how do we prove this. There's a second theorem that we can prove, which is, let's talk about what if K comes from a finite collection. Now, finite collections are easy, right? I tell you, it's one of L1 to Ln, okay? You just have to. Now, here actually, Angluin in her 79 paper proved that actually here you can actually solve identification in the limit. So if you can solve identification in the limit, we say, well, just solve identification, and once you identified, generate. So what more could we ask for? There is something more we could ask for in the case of finite collections, which is, in the case of identification, we can't give an a priori bound. I can't look at my language collection, C, and output a number, T of C, which is how many steps I'm going to need before I succeed, right? It's going to happen eventually, but I can't know when. And that's sort of clear. Like, say, the example with just L1 and L2. L1 is all strings, and L2 is all strings of even length, okay? And suppose I claim there's a bound on how long it will take me to identify these correctly. Well, then the adversary just outputs strings of even length until I'm beyond T of C and asks which one is it. And if I say it's all strings, they say no, it's even length strings. If I say it's even length, then their very next string is odd. Right? So the adversary can delay my knowing the answer arbitrarily long. I can't put an a priori bound. But for generation, you can actually. For generation, you can take any finite language collection, inspect it, and put a timer and say within T of C steps, no matter what your enumeration is, I'll start generating correctly. I mean, here it's easy. I just start generating even length strings immediately. So this particular example poses no problem for us, but that's true for any collection. Okay. So that's the second thing that we can check. All right, let me start talking about how we do this, which hopefully will make it a little less mysterious what's going on here. Okay. Questions of the premise? Yeah.
How does TFC look like? Do you have a?
Oh yeah. So in the end, I'll actually be able to describe what TFC, or at least what our upper bound. We do actually give an upper.
But it's not just, I mean, just n is good enough, or you really?
No, it's the collection. Yeah.
So for any n and any t, I can construct a C that will.
Correct. Correct. Yeah, I could find a language collection that could. Yeah. No, it's a property of the language themselves, which at the end I'll slip in the sentence. I can sort of say it in one convoluted sentence, but I'll do that at the end. Yeah.
So wondering, so you have evaluation. Sorry, you have like generation, you have recognition.
Yeah.
You think about the problem of estimating the probability of this thing coming out?
No, so it's a nice question, yeah, because we've sort of deliberately kept probabilities out of this completely.
Because you are talking about a distribution, so it's a natural question.
I would have to find a way to put the distribution in. Right now, I have an adversary that's doing worst case generation, worst case examples. So this is very much so far a worst case model. You could say, imagine that an adversary has to somehow commit to some distribution that it uses. Yeah, it'd be interesting to think about, like, you would want to say like the distributional assumption would be a constraint on the adversary. And so the adversary would have to say, like, I'm committing that the distribution has to be of some form, and then we could ask, could we even do better? Yeah, that's interesting. Yeah. Yeah, but we haven't thought about that because we really thought about this. Okay, so let me start with, I feel like the easiest way to get into this is like some things that don't work, because like you start thinking about this problem, you're like, okay, I think I see what's going on. And the first couple of things that you think are going on is not what's going on. So it's worth dispensing with those. So the easiest way to see why generation ought to be easier than identification is to think about the following example, okay? First of all, it doesn't matter if we have strings, right? Strings is the motivation, but like any countable set, ground set, like languages are subsets of some countable set. This countable set could be the integers. It's fine. Just think of those as the indices of the string. Okay. So let's use integers for our examples. They're much easier. Suppose my languages consist of all infinite arithmetic progressions for this first example. Okay, just so we can all kind of have an example to play with. Both doubly infinite arithmetic progressions and one-way infinite arithmetic progressions, right? So either left anchored going this way or infinite both directions. Okay, the adversary says it's one of those, and they begin enumerating elements of this infinite arithmetic regression. Now, for identification, Gold's theorem, you can't identify in the limit for an infinite arithmetic regression. And the reason roughly is that the adversary will keep going this way until you guess that it's the thing anchored at -3. And the instant you guess that, it'll add -6 and then keep going this way. And eventually you'll have to guess it's the count by 3 is anchored at -6 or else you'll be wrong. The instant you guess that, it puts in -9 and keeps going. That's basically the proof of Gold's theorem, basically. Okay. But for generation, look how easy this is. I showed you those two things, and I asked the audience, please generate another thing from this language. And if you all say 9, you would be correct, because any infinite arithmetic regression that has -3 and +3 has 9. So once you see two things, you can generate. So certainly this language family, like obviously we eventually want to build up to all language families. That's what's a little mysterious about this result. But certainly this language family, generation is possible after 2 examples. Right? This is a particularly easy set of things. It's sort of like I say, I'm thinking of a secret convex set in the plane. I'm going to show you points. I want you to figure out the convex set. You're like, well, that's hopeless. It's like, yes, okay. How about I just want you to generate from the convex set? Once I put down, like, I put down these 3 points, you build the convex hull, you can generate from inside that triangle forever. Or frankly, 2 points, you can generate from the interval forever, right? So it feels like that's part of what's going on. Yeah.
Not
Yeah.
then it is identifiable.
Then I think it's identifiable. Yeah. Yeah. No. So right. That would be an example of a thing that actually is it.
Oh,
Yeah.
why? Your negative example seems to be referred to as only one way. You can always move it earlier.
But you eventually have to stop, because if it's one-way infinite, there is actually a left endpoint. And so after finite time, the adversary has it. After some finite time, the adversary has output the left endpoint. I think
I'll just change my mind and it'll still be consistent.
I think the order of quantifiers goes the other way. Like the algorithm doesn't matter when it wins, right? So this is actually useful. Like suppose I know it's the count by 3 arithmetic regressions. We would need to, there's an extra step about infinite descending chains in the sense that if it's arbitrary spacing, I need to make sure I run out of my spacing. But let's just say count by, what are we? We have count by 6 arithmetic regressions here, yeah. So if I just keep moving left by 6s every now and then, the order of quantifiers is that the adversary has to pick a language, K.
Based on your algorithm, right? So
Based on your algorithm. It sees what your algorithm is going to do. Based on your algorithm, but suppose my algorithm is like, just guess it's the one anchored at the leftmost thing I've seen. Say that's my algorithm. What can the adversary do? Because there will come a finite time when it has to output its left endpoint, you'll be right forever. Yeah. Oh, it can make it go as far as it wants, yeah. But you will, and that's the key thing about identification in the limit. It's not asking very much, but even so, it's impossible because you can just keep going left forever. So yeah, so the secret convex set in the plane, it's so obvious I can generate from the convex hull. It suggests maybe, and I bring this up because it's actually a misdirection. Like this will not actually be sufficient to solve our problem. But it's sort of the thing you start trying, and we need to dispense with it. It seems like we ought to have, like, that language generation is sort of about closure. It's about saying, given a finite set, like, why could I do this? Phrased in abstract terms, if I took the intersection of all languages that contain these 2 points, all of them also contain 9. Right? And like closure is one of our favorite mathematical operations, right? The closure, the subgroup generated by a set of elements is the intersection of all subgroups that contain those elements. The convex hull of a set of points is the intersection of all convex sets that contain those points. So why not say, let the closure of S be the intersection of all Li in my collection that contain S? It's always safe to generate from the closure, because whatever the language is, it certainly contains the closure. So we hoped, once we started suspecting this theorem was true, maybe for every instance, once T is large enough, the closure has something that S doesn't. And I just generate from that. Unfortunately, so actually, this is sufficient for the finite case. For the finite case, eventually the closure will be bigger than the set. And I just, in fact, eventually the closure becomes infinite in the finite case. So it was enough for that, but it doesn't work for what we need. And so I'll just show you a quick example. Imagine that I have a only slightly more complicated countable set of languages. My slightly more complicated set is all infinite arithmetic regressions union an arbitrary finite set. So I have an infinite arithmetic regression, a beautiful object, and I pollute it with just a bunch of finite set of points that obscures the structure, right? So I start building that, but then other stuff shows up. Okay, so now for any finite set, the closure is equal to S. Because whatever you've seen, it could just be the finite set V, right? It could be that all you've ever seen so far is this finite set. And so you're getting no other information. So there is no extra elements to generate in the closure. Despite that, you actually can generate from this collection in the limit. It's not going to be via the closure, and you're never going to actually know what the thing was that you were generating from, but you can do it in this case. Okay, so we need something better than closure. Here's a second thing which also doesn't work, but this one at least is on the path toward the thing that does work, so it's worth going through, okay? Second thing that doesn't work. It's going to really lean into the idea that this is a countable collection of languages, and this is sort of, it feels like this is something you sort of have to use. Here's the idea. We're going to start with the hypothesis that L1 is K. It's one of these languages. So let's sort of stop freaking out and go, let's just go one by one, which we'll try L1. If it doesn't work, we'll try L2. If it doesn't work, we'll try L3. So we're going to start with the hypothesis that L1 is K. And we're just going to keep maintaining this hypothesis as long as what I've seen is a subset of L1. In each step that holds, I'm going to output a new string from L1. And the way I do that is I just start enumerating all strings. And eventually I'll crash into one that belongs to L1 because L1 is infinite. So I can do that with an algorithm running in finite steps. And if we ever get to a step where the sample is not from L1, I just update my hypothesis to L2, and I keep going. Now, this actually is such an appealing idea that when you first think of it, you spend a little while going, I think we're done, right? Like, it feels like there's a proof here, which is if Li is not equal to K, then eventually I'm going to learn that fact, and I'll move on. So I'll move on eventually from Li to Li plus 1. K is equal to Lz for some z. And so eventually, step by step, I will arrive at Lz. And once I'm there, I'll never move on, because obviously nothing will ever prove me wrong. And that's the moment which I start successfully generating in the limit, right? It feels like, so that's, even for the finite case, that is not a proof, it turns out. Not if I go in this order. And let's see. So yeah, so we can also tell that for the infinite case, it can't be a proof, because if this worked, it would also solve identification in the limit. Right. I mean, the word generation here is sort of incidental. I could have said identify, and I would have. So something's wrong here, right? But it just seems so appealing. Like Lz is here. It's like it's L sub 100. It's just 100 steps away. The adversary will eventually cause me to refute all my earlier hypotheses. So what? Yeah. So there's something wrong with this. So we can pause and reflect on what might be. We got stuck on this long enough that we added a section to our paper that's like, here's why this doesn't work, because we like maybe other people will get stuck where we were. I guess
the post at every step, like right. So it's L1 and L2 and L, they're all nested, right? So it can always decide.
They might be nested.
Yeah, so they become bigger and bigger. So then the adversary can always just change the goalpost as they go, right?
I mean, the adversary does. I mean, the one thing the adversary is stuck doing is it has to commit ahead of time to what K, right? It says, it's like I'm generating from L100. I don't tell the algorithm that, but now it can choose that by inspecting the algorithm. But in some sense, the algorithm ultimately the adversary does have to be generating from the language. But the nestedness is somehow key to what's not working, and it's the following. It could be that L5 is the real one. It could be L2 is a proper superset of L5. And so the positive examples only thing is a real problem, because you'll never move on from L2, because L2 is bigger than L5. And so everything you see is consistent with it being L2. In fact, L3 could be literally everything. It could be all strings. You'll never move on from the set of all strings. So you'll get stuck early. And this is actually identification in the limit, right? Were it not for this, identification limit would be possible. So this is a big problem. And in a sense, it's actually the problem of hallucination, right? It's that in the end, I mean, and again, obviously this is an extremely abstract model, so I'm not trying to tie this to any real hallucinations that are really happening in language models, but it is the case that it does sort of just make the sort of centrality of hallucination as a problem kind of clear, which is the problem is that you might think you're in a language that's bigger than it is and keep generating stuff that's invalid, right? Okay, so now let's actually start talking about what is actually. And again, obviously, I'm only going to be able to like sketch how this works in the time we have here. But okay, so let's make this a little right. So pictorially, what's happening here, right? So like just as a kind of visual mnemonic here, the languages may be arranged in order. These are all the possible strings indexed by the natural numbers. I have a blue dot, so this one has strings 1, 3, 5, 7. This one has 1, 5, 7, and so forth. maybe this secretly is the true language. My strategy has the right. I'll say that language LI is consistent at step T if ST belongs to it, right? So initially the algorithm says this. So in fact, everything is consistent among the first 7. Then the adversary says this. That knocks out L1. So now I know L1's inconsistent. Maybe I move on to L2. Right. And you see the problem that L2 is maybe a superset of L5, the truth. And you would never move on. And of course, even if you somehow miraculously moved on, there's L3, which is everything. And so if I have to move on, this is where it gets worrisome. If I have to move on, it's like I'm going to have to move on beyond L5. And then I'm lost. Then I'm just drifting out to C forever because I've passed the correct language. What do I do now, right? That's the problem. OK, so it does suggest something, which is, and let's get back to nestedness, your point about, it does suggest that we should look for not just, if Li is a subset of Lj, it's safer to generate from Li than Lj. Right, now these are all infinite sets. So I'm not talking about small in a finite sense, but it does suggest we should look maybe for minimally consistent languages. And L such that L is consistent with ST, and there's no consistent L prime that's a proper subset of it. If I can generate from a minimal one, maybe that's, at least I know I'm not, somehow. But the problem is that the sets could form an infinite descending chain. So there is going to be no minimally consistent one. There's always a proper subset of it. So that doesn't by itself work. But that finally motivates, after all these false starts, the definition that once you find it, and once we found this definition, everything just started unraveling in a really clean way. The definition, which is sort of hard to find ahead of time, but is exactly what we ended up needing, is let's say a language ln in my list, right? The enumeration, the ordering matters. Ln is critical at step T if it's consistent at step T, and if L sub I is an earlier language, is also consistent, then Ln is a subset of Ln. So basically, Ln is minimal if you look forward in the sequence back to the beginning, right? It's minimal for the finite prefix that goes from L1 up to it among the consistent languages. Now, critical at step T, it can change with T because it depends on consistency, which depends on what you've seen so far, okay? But it basically says a critical language is sort of like the sequence of languages passes through sort of the eye of a needle here, which is like, this is a particularly thin language because it's a subset of all the earlier consistent ones. Now, okay, obviously we can define lots of things that might not exist. In fact, critical languages exist. For one simple reason is that at step T, there's always at least one critical language, which is the lowest indexed language that's consistent in step T is going to be critical because, this holds vacuously. There's nothing consistent before. So there's at least one critical language. Now, the key question is like, will our true language eventually become critical? It doesn't have to be critical early on. Like if you ask like right now, is it critical? The answer is no, because yeah, it's a subset of L2 and a subset of L3, that's good. And L1 is out because it's inconsistent. But L4, it's not a subset of L4. So currently our true language is not critical because it's not a subset. L4 is consistent, not a subset of it. But I know it will eventually become consistent because L4 doesn't have element 5, right? And so eventually L4 is going to become inconsistent. Right? I don't know when that'll happen. It could happen arbitrarily long from now. But eventually L4 is going to become inconsistent. And that's actually a proof that although we can't say when, there is some step T plus, such that for all T greater than or equal to T plus, my true language LZ is critical at step T. Right? And the reason is just for every earlier language that it's not a subset of, there's some string that LZ has that it doesn't. There's some finite time, right? Here's like the one and only place where we're using the fact that the adversary must enumerate every string of the language. There's some finite time when the adversary must first enumerate this VI that belongs to LZ, but not this earlier language. And just take the max of those steps. At that point, we've knocked out every earlier language that's not a subset of. And so it's a subset of all the other ones. And so LZ eventually becomes critical. And that's like going to be, right? So now let's talk about how we use criticality. Criticality turns out to be the definition that actually gets us somewhere. Here is now an algorithm, although in naughty sense, let's start with an algorithm that's augmented by some oracles that can do things that algorithms can't do. So it'll be a rule. And it'll be a well-defined rule in the sense that it's a function that takes what it's seen so far and outputs a string. So it's perfectly well-defined. It's just, it's going to need some oracle help that we'll then get rid of second. Okay. Here's the algorithm, actually. And the algorithm now once you have a definition of critical, the algorithm gets very short. In step T, we're only going to consider L1 to LT. Okay, so we have this widening window as time goes on. And that's fine. The widening window will eventually get so wide, we're eventually including LZ. In this window L1 to LT, we're going to say L sub NT. So NT is the index of is the highest index of a critical language in L1 to LT. Okay, so there's some critical languages in here. We've established there are maybe several of them. Take the highest index. We're going to generate, our algorithm is just in step T, compute NT, and generate a string from L sub NT minus ST, right? Can't be what you've seen so far, but just generate some other string. That we can do by just walking our way up through the language until we crash into one. I want to claim the strategy achieves generation limit. And I say proof sketch, this is actually just the proof. We'll say T star is the max of two things. One is Z, where the language occurs. And two is T plus, the time at which that language becomes critical. So beyond T star, we're considering LZ, and LZ is critical. Therefore, when we find the highest index critical language, it's an index that's beyond Z. And this highest index critical language, when it looks backwards toward index 1, it's a subset of every earlier consistent language, including LZ. So this thing we're generating from is a subset of LZ. And this is the whole key point, right? That it's critical, our language is consistent, and it comes later. So therefore, any string from here must also belong to this. And so I'm generating the limit, right? And I've named the time at which that's happening, T star, the max of these two things. Okay, and so you can kind of visually see what's going on here, which is as we move out down this list, there's this kind of like receding infinitely into the distance, or these thinner and thinner infinite subsets, right? And I keep chasing them further and further. At some point, I don't know when that point was, I actually got beyond LZ. I don't know when that was. So I have no idea when it was that I started winning. But at some point, because I'm moving on forever, I'm getting to thinner and thinner sets, and I'm generating from them. So I will generate an infinite set of things. And eventually, they will all come from the secret language, right? Because the adversary, right, no matter what it does, it had to actually generate from some language on this list. That language on this list had to come at some finite time. Okay, so, and that's the sense in which, right, we sort of start with hallucination early on. What we end up with is this kind of more mode collapse kind of thing, in which we're just getting to a thinner and thinner subset as we get more and more complex. Right? Okay, a final issue, and I have like 5 minutes, so I'll just kind of, recognizing if ln is critical requires determining if ln is a subset of Li. And I can't do that with a finite number of queries. So, so far what we have as a result for algorithms that are equipped with subset oracles. The Angluin Gold results there's still impossibility here. So we still have the same distinction we had before, but we might want an algorithm that actually runs in a finite number of steps. And because I have 5 minutes and I could either tell you about that or I could tell you about the finite case, let me talk about the finite case, which is mainly because this part, while interesting, is harder to parse in real time. I had a couple of slides that show that what we're going to do is basically work with finite prefixes of the languages, right? So just as we were moving this way, we're also going to move this way and only look at finite prefixes. And we're going to change the definition of criticality to only apply to finite prefixes, and that will be actually good enough, right? So we have to like morph the definition of criticality. But let me actually skip that to tell you about the finite case. Okay, so remember, the point of the finite case is identification of the limit is possible also, but here we can do identification in a sort of uniformly bounded amount of time. I can look at the collection, write down a timer, and say, I promise you within this many strings, I will generate this language. Okay, this really will use the closure operation. Our theorem is going to be that after some finite time, the closure of your finite set will become infinite. And at that point, you can just generate, at that point, you can cease all input from the adversary and just generate from the infinite closure. Okay, that's the plan. Here's a proof of why that's going to happen. And actually, this proof is short. Like this proof operates totally independently of everything I've shown you so far. It's like just a totally separate fact with a separate argument. Okay, here's roughly the whole argument. If the intersection of all the languages is infinite, like say the adversary was foolish enough to give you a collection L1 to Ln whose mutual intersection, n-way intersection was infinite, then you don't need any examples. You just generate from that infinite intersection. So let's assume it's finite. So therefore, for every subcollection, right, there are 2 to the n different subcollections of languages. Each one, or to the n minus one if we don't count the empty one, the mutual intersection in each subcollection is either finite or infinite. The one-way intersections are infinite because each Li is infinite. The n-way intersection is finite, or else the whole thing would be trivial. And there's some like set system here of like all the ones where the intersection is finite, a kind of upward closed set system. Okay, so consider that upward closed set system, all subcollections that have finite intersection. And let M star be the maximum cardinality of any of these intersections. So when I said originally, I could tell you what T of C is in one convoluted sentence. T of C is the maximum cardinality of any finite intersection, finite mutual intersection among the n languages. That's what I need. Which actually raises the interesting question of like, if I took, say, the first n finite automata and asked, what is the largest finite mutual intersection of any set of n-state finite automata? That's right. It's sort of, that's the kind of question you're asking here. Obviously, these are going to be astronomical bounds because we're talking about the limit, but right, but that's what it is. Okay. Why is this good enough? Well, because say I run for m star plus 1 steps. So the adversary produces a set ST. Let's ask about the closure, right? The closure is an intersection here. It can't be finite because then it would have cardinality at most m star. So it must be infinite, and therefore I can generate from this infinite set. Okay, and with that, I will wrap up. So our point is, if we start from this original sentence that we want to produce in 17 before, it turns out to be a mathematically richer way of asking. Like, I think we expected we would ask this and then dispose of it very quickly. Turns out to kind of, there's some mathematically deep vein you can actually mine once you ask this question, because it turns out to be possible to generate from an unknown language, knowing only that it comes from this countable loop. And it uses the strategy that kind of like passes through hallucination down to, there's some brief sweet spot where it actually has the right answer, but it doesn't know it. So it keeps going and just has thinner and thinner languages, right? It sort of was reminded of, so my colleague, Cristian Dănescu Niculescu Mizel, who works on conversation on social media, reminded me of a paper I always enjoyed of his from 10 years ago about how people, when they join an online community, learn the vernacular of that community, the slang, the idioms, and so forth. Because the way it works is initially they misuse the idioms, but he showed in the data that as people age, not only do they stop misusing the idioms, they don't adopt new ones. They just keep using the old slang from when they joined, which makes them sound old, and they don't pick up the new ones, right? This is effectively what our algorithm is doing. It starts out being way too expressive, but eventually it becomes so conservative in what it's saying that it just goes to thinner and thinner subsets, right? And so one interesting question that I'll leave you with, I mean, there are a bunch of interesting open questions here, obviously, but one interesting question I'll leave you with is there some way to formalize the idea that every solution to language generation limit has to work this way? That it has to somehow collapse onto arbitrarily thin subsets of the language? Or is there some better way than we found that actually generates in some much more robust sense from the full language, other than what it's seen, obviously? Lots of other interesting questions. I'm out of time, and so I'll stop there. Thanks very much.
So I think I'd argue that maybe the more thing they really want to do is not generation, but given a prefix, find a legitimate completion that's in the language.
Yeah.
Where does that? I mean, that seems a bit part like closer to identification in terms of partners. So like, where does
That's
that?
a great question. We actually in our paper we have a section that talks about what we call prompted generation, which was a whole extra piece that I didn't have a chance to talk about. Yeah. So you imagine that in every step, we have some results for this. The adversary shows you two things: an example, and also it shows you a prompt. And your goal is to output something that completes the prompt and stays in the language.
That could be repeated. I mean, there's no repetition issues there. I mean, I'm allowed to repeat.
We're allowed to repeat prompts. Yep, absolutely. Well, the adversary could even repeat examples in our thing. Oh, the learner could repeat. You can certainly see the same prompt again, but if the thing you said before is taken, maybe you have to move on to a new one. Actually, if you don't have that, then roughly speaking, the answer is you can still do that. Because once you have this, I mean, the structure of critical sets is really powerful, right? If I'm generating from the last critical set and I'm working my way up, I say, okay, I have this prompt. If I commit to the idea that this last critical set is safe to generate from, if you give me a prompt, I'm going to walk my way up this language until I get to something that completes that prompt, which you promised me is there. And yeah, so the prompting matters. So there are some things that are going to be hard. For example, if I can't repeat answers, then I have a problem with like not knowing whether there's another one to generate from. But if I'm allowed to repeat, then yeah, then I basically, right? Because you have to think like, I'm looking at the last critical language in L1 to LT. And you've told me there's something that completes the prompt, so I'm just going to say it. Now, I could be wrong if I'm not yet at a critical language that's beyond the true language. But if I'm truly at a critical language that's beyond the true language, and you tell me I want you to complete this prompt, the thing I generate will come from that. So we can talk more, but yeah. So it depends exactly how you set up the problem. But there are cases where prompted generation is not actually harder than just on straight generation.
One more question. So thank you for the thought-provoking talk. You said two things that I didn't quite understand. In the example of arithmetic progressions, said adversary might sort of change. But you also said that you have to choose it. It fixes ahead of time. And the second thing is maybe there's linguistic shift. Maybe it's, but there is a real language that you care about. It's an index in that list.
Yes.
And the adversary can't change that after you've made some choices.
Yeah.
I just didn't understand.
Yeah, no, and it is true. Like, it's a fair point that the way I was describing that sort of made it sound like the adversary was changing their mind. Actually, the adversary does this as a simulation in its mind. So it says, and then, again, there's the problem for identification, right? It says, you have to hand over the algorithm to me, the adversary. I'm going to hand simulate the algorithm, see what happens. And I'm going to start going forward by 6s in my simulation until you say here. And then in my simulation, I'll say, okay, in that case, new plan, I'm going to add -9 to this. I will again simulate. At some point, you will say -9, at which point I say, okay, in that simulation, I'll add this, and so forth. And so I'm going to, after I do that analysis, I will commit to the language because I know what you're going to do. Yeah.
Yeah.
And then I totally agree with your point. A model where there's like linguistic shift, where the language is actually changing as you're studying it, which of course may happen with your language. Yeah, that's obviously not covered. Like here we're saying there is a language and we're trying to find it.
Okay, let's thank the speaker again.
All right, thanks very much.
And we'll resume at 10:35, and please feel free to